let's see what we can do. So last time was discussing the field-oriented vector control, and we stated that, if you recall, the torque was equal to 3/2. This is due to the transformation. P/2. This is due to transforming the mechanical speed to electrical speed. And if I'm describing the torque in terms of the rotor variable, it was lambda QR I dr minus lambda dr I QR. Yep. Now we said that under field-oriented control, which means that we are assuming we can manage to point the flux of the rotor toward the DRE. So in this case, we'll have lambda QR E is equal to 0, and lambda DRE is equal to lambda R. And at first, we assume this one to be what? Constant. So if this is the case, automatically this term, so this term will come at 0. Why? Because lambda QR is equal to 0. Yep. So TE will equal to 3/2 now, P/2 minus lambda VR IQR. Now, in general, we need to represent the torque in terms of the stator variable. Why? Because I can measure the stator variable, but the rotor variable is difficult to be measured. So I need to substitute instead of IQR by IQS. So from where we will go to lambda QR, which was equal to LR IQR plus M IQS, correct? And this one equal to 0. So from here, because lambda QR is equal to 0, so from here IQR will equal to minus M over LR IQS. Now if I substitute this one here, we will end up with TE is equal to 3/2 P/2 M over LR lambda DRE IQS E. And E here for what? To represent what?
Synchronous.
Yeah, the synchronous rotating reference frame. That all the quantity now is represented or referred to as synchronous rotating reference frame. Now the same thing here, we can say that lambda dr is equal to LR IDR plus M I ds, and we know that this one will equal to 0 under the field-oriented vector control. From VDRE will equal RR IDRE plus d by dt of lambda DRE plus here omega minus omega R lambda QRE. This one is 0. This one is 0 due to the assumption that I'm having a constant flux. And in the end of the day, either I'm assuming a synchronous, square cage rotor or shorted rotor in the one type. So IDR will equal to 0. So here I will have what? IDS. Now in terms of the current, the torque TE will equal to 3/2 P/2 M square over LR IDSE IQSE. Good. And we stated that now the torque proportional with IDS, IQS, and I think last time we stated that IDS is the flux component of the stator current, while the IDS is the torque component of the stator current. So is the torque component of the stator current. Which means that the field organ inductor control managed to transfer the complete control problem of the induction machine to be as easy as the separately excited DC machine. Yes? Good. So now someone will say, if you remember the block diagram we plot, we need the IDS, the reference current. Without it, I cannot calculate what? The IDS. Yeah? So someone will say how I can find this one. How I can find this one. For that, let's take the following example. And it should be good to discuss the following example. So let's assume that we have 400 volts. So this would be example. $400 volts, 50 hertz, 1370 RPM, Y connected square cage induction machine. Has the following parameters, let's say. RS equal to 2 ohm, RR dash equal to 5 ohm, XLS equal to XLR dash, which equal to 5 ohm, and XM equal to 80 ohm. Now the machine or the motor is controlled by a current regulated pulse width modulation voltage source inverter operated at rotor flux oriented vector connection. Now we need to find the IDS reference for the vector control. Just like that. I need only to find what? The reference IDS. The reference IQS will come from where? From the speed controller. Huh? Do you remember? Simply here. This will be omega R minus the reference one, this one, omega R. Then I will have a PI control. Now here I will have the torque reference. After that I will divide it over 3 over 2 P over 2 M squared over LR IDS reference in order to calculate what? IQS reference, correct? Now if I have the current IDS reference, IQS reference, I can use the QD to the ABC with the knowledge of theta in order to calculate IA reference, IB reference, IC reference. After that, I will use the hysteresis current control in order to generate what? The gate pulses. Yeah? So without knowledge of the IDS reference, I cannot proceed. Just now remember.
ليش ما مثلا hysteresis control نحطه قبل ال QD to ABC؟
Okay. In the sequence rotating reference frame, all the alternating signal is seen as constant. Yes? Now, if the signal is seen as constant, there is no meaning for the hysteresis control actually. The hysteresis control is powerful if there's oscillation. Yeah? Now, if there's no oscillation, if the reference is constant, the BI control will provide more straightforward to design. But remember, the hysteresis current control is a non-linear control. While the BI control is a linear control. Now, which one is more easy to deal with? The linear one or the non-linear one? The linear one. To deal with in terms of the design. Huh? In terms of the implementation, the hysteresis control is very simple. Decide the band and that's it. But simply this will result of what? Variable switching frequency. Yeah? Which means that in the end of the day, how to design the filter will be complicated. Yeah? But if I'm using a passive modulation with a PI control, in this case, I know the switching frequency. So according to that, I can design what? The line filter. I will discuss that after.
أي reference constant.
Now, the question was, why I'm not using the hysteresis current control before the transformation?
Oh.
Yeah? Now, before the transformation, I'm having what? In which reference frame I am?
QD.
In the sequence rotating reference frame.
Okay.
So, any signal that rotates in the same speed is seen as constant.
Oh, okay.
Yes? So if the signal is constant, if the reference is constant, why I will use hysteresis? There is no reason to use hysteresis. Why? Because I can use the PI control. Yeah? The PI control is more powerful if the reference is constant. If the reference is alternating, in this case, the PI control will be what? Not accurate. That's why we'll go to the hysteresis current control. But simply here, the idea is what? Is to calculate the ID reference of the controller. Yeah? I need the ID reference to proceed. So, how I can find the IDS reference? Now, if I need to operate the machine, I will operate it at what? At the rated flux. Correct? So, the first thing I need to calculate the rated condition. From the rated condition, can I find the rated DX current? Let's see. The first thing, the transformation that we are using is amplitude invariant, correct? Do you remember when we discussed the 3/2 or sometime I can modify? The 3/2 will provide what? Amplitude invariant, which means the maximum value in the ABC is equal to the maximum value in the DQ, correct? Yes? Good. So simply this means that if I can calculate IS, then this one should equal to the square root of IQS squared plus IDS squared, correct? The amplitude. Yes? The second thing, do you remember omega slip was equal to what under vector control? 1 over tau.
tau.
R IQS
IDS.
over IDS. So simply now I'm having two equations to unknown, yes? Yeah? So the first thing I need to calculate IS, and the second thing I need to calculate what? Omega slip. Yes? Now, which one is can be given with no time? Omega slip. Why? At rate condition, this machine is rotating at 1370, I think.
Yeah.
Yeah? So simply I can calculate omega slip from here. Yes? So omega slip will equal omega s minus omega r. Correct? Now omega s will equal to what?
2 باي 50.
This is the synchronous.
Yes.
Yeah? This one is 2 or 4 poles.
4.
4.
1500
Yeah. So NS will equal to
1500.
1500.
Minus
Yeah.
1370.
So NS, if we calculate NS, it will be 1500
Minus.
minus
1370.
1370.
130.
Okay, so from here we can calculate the N slip, and if I need to calculate omega slip, it will be
130 2 pi s t.
so this one NS and slip multiplied by pi over 30, and if we do the math, this will equal to what? Calculate it. Any calculator?
Yes.
Calculate. I think it's 27.226 rod per second. Is it?
13
Yeah. Equal to what?
13.61.
But this one mechanical. Yeah. 13.61.
61.
This is a rod per second. This is mechanical speed. This one is what here? This is the electric. Yeah. So I need to multiply it by what?
By 2.
B over
B over
P over.
2.
So in order to calculate the electrical one, so this will be equal to P over 2 multiplied by 13.61, which is 20 rod per second. So this is mechanical.
بس دكتور احنا بنفترضها 4 فولت ولا
Okay. Now this one is what? In general, the synchronous speed is what? The closest speed to this, to the NR.
Yes.
The closest one is what? 1500. And it's written here, it's 50 hertz. Yeah? So 50 hertz, this means that the synchronous speed is 1500. If the synchronous speed is 1500, we know that NS is equal 120F over P. So from here, we can calculate P, which equal to 120 multiplied by 50 over 1500, and this will equal to 4. But you don't need to do that, it's already known. Yeah? 3002. Yeah? If this one 1754, in this case, this would be 60 hertz. And this would be a 60 hertz. Okay. So now we have what? The first equation. So the first equation from here. We know that it was 27. 27.22 will equal 1 over tau r IQS over IDS. Now, tau r equal to what? LR over R. Correct?
Yes.
Now, RR is given. What about LR?
We have the
We have the X. We have the reactance. Huh?
Yes.
And remember, those calculated at which frequency? Yeah, so we know that X is equal omega L. So if I need to find L, it will be X over omega.
Yes.
Yes? And LR will equal to what? LR plus LR. So it it will be this one plus this one over omega.
85 over omega.
Yeah, and R is already here given.
Yes.
So if we do the math, then this will equal to, I think I calculated somewhere here. Yeah, 0.0541 second, because this one is time constant. Okay? Good. Okay. Now, what about IS? I need to calculate this one. I need to calculate this one. So from the pair phase equivalent circuit, here I'm having the RS, XLS, XM, XLR dash, and after that I'm having the R dash over S. Now this one is given 2 ohm, this one is given is 5, so J5 ohm. This one is given, so J 80 ohm. This one is also given J5 ohm. This one will be 5 over S, correct?
Yes.
5 over S. Now, if I need to calculate S, it will be equal to omega S minus omega R over omega S, and if we do the math, this will equal 0.0866. Now, the voltage here is phase. This one will equal to what? 400 over square root of 3. So if I need to calculate IS, which is this current, what I will do, my son? I need to find Zn, huh? This Zn. Can you find Zn for me? Yeah. So the first thing, I will calculate the parallel of the J80 with the rotor. Then I will add it to what? To the stator, and I will find the, let's say, the Z inputs. And if we do the math, this will equal to 49.864 with angle 42.13 degree.
بس هو لازم الجوز قبل ال 5 over 0.0866 يعني لازم أول إشي في كمان جوز بعد ال
You mean this one is package? Yes,
Yes.
it's package. It's package. Of course.
ماشي ممكن
I said that this one is parallel with that one.
دكتور ما بنقدر نستخدم البير فيز كونسبشن.
You know, here we are going from scalar control to vector control. Scalar control has approximation. Yeah? Here, the approximation is not valid.
You can.
No, I need to calculate the exact. Yeah? Why? Because I'm using more sophisticated control, more advanced control. Let's say. So now I can find IS, yes? IS will equal to 400 over square root of 3 over 49.64 with angle 42.23. So this will equal to 6.59, I think. 6.549 with angle what?
Minus 42.
Now this one, RMS value or maximum value? RMS value. And this relation?
Maximum.
The maximum. The peak, the maximum value. So simply, I need to multiply it by square root. So IS, the maximum value, will equal square root of 2 multiplied by the IS, so this will be Let me just the way I did here and take this one is 4.63. So now do the math.
ست فاصلة خمسة أربعة سبعة.
6.54.
As amplitude. Okay. Now let's see what equation we have. So this is the first equation, huh? And this is the second equation. So let's write it here. So the first one,
كانت
IS was 6.
6.547.
Will equal the square root of IQS square plus IDS square. The second one was omega slip to 7.226 equal 1 over 0.0541 IQS over IDS. So this is the first equation and this is the second equation. I need to solve with respect to what? So simply, if I simplify this one here, I can say that IQS will equal this one multiplied by this one multiplied by IDS. Yep. If I do the math, this will equal 1.473 IDS. Now I can put this one here.
محل اي
Here.
بنطلع
اي كيو اس.
بنطلع اي.
Yeah. Here. Let's do this one here. Yeah. So simply, or someone say, square this one. If I square this one, this will equal 2. If I square it, square it.
42.
Square 6 point this one
42.6.
will equal 2. Square this one. So 2 point. So it will be 3.169 IDS square. Correct? So IDS will equal to what? The square root of 42.86 over 3.169, and this will equal to what? If you have the 3.677. According to Suleiman. Okay? Are you sure it's 3?
Yes.
True. Ampere. So this is the current that I need in order to or the reference current that I need in order to fulfill the vector. Good. Now let's return to the question, which is, can I use the PI control instead of the hysteresis current control? Now, if I need to use the PI control, I need to operate the controller in the synchronous rotating reference frame. So for that, if this is omega R reference, omega R, after that here, I will use a speed controller. And by dividing here, I will have the IQ reference. This is the ID reference, and already we know how to calculate it. So now we have the ID reference and the IQ reference. So someone will say it's very straightforward, do the current control here. Yeah. So simply, this means that I will compare this one with what? With the actual IQ. With the actual IQ, correct? Then I will use a PI control. The PI control, the current control, the output of the current control is what? The input is current. So output will be what? Voltage. Yeah. Current control, the input is what? Is current, the output is what? Volt. So this will be what? VQ reference. The same thing here. I will compare it with the actual ID. Then I will use a PI current control. See here what will have? VD reference. Now, if I'm having the reference Q and the D voltage, I will do the transformation from QD to the ABC, and here I will generate what? VA reference, then VB reference, then VC reference. Those will enter to where? No, to the pulse with modulation, correct? Yeah. And I will generate the gate pulses for the 6 switches, 1, 2, 3, 4, 5, 6.
The inverter.
For the inverter. Yes, thank you. Now I'm using a BI. This is a BI current. From here to here, which reference frame I'm considering? The QD. The synchronous rotating reference frame. So it's QDE, which means the reference frame is rotating what?
Synchronous.
In synchronous. Okay. Now, the machine electrical variable is rotating by which speed? The machine electrical variable, I mean the current, the voltage, the flux, is the electrical variable. In synchronous speed. So, if the variable is rotating in synchronous frame, and my frame is rotating at synchronous speed, so according, referring to the rotating frame, they are seen as constant. Yes? Yep. So if they are seen as constant, the PI control is powerful if the reference is constant value. It's very powerful for them. And from here to here is the ABC. Reference, correct? Why? Because the machine understands only ABC. Now, until here I did not finish, by the way.
You have taco generator.
And this is again, this gain K is equal 3 over 2. 3 over 2 P over 2 M square over L. Correct? Good. Now until here we did not finish. The first thing I need to calculate for transformation here, I need theta E. Yeah?
Yes.
Okay. So the first thing here, I have IQ, I have ID, so I will take IQ and ID. Then I will evaluate 1 over tau R, IQ over ID, correct?
Yes.
And this will generate what? Omega slip that I will add to the omega R. Then I will integrate in order to find theta, correct? This is the first thing. So, the second thing, I need to calculate IQ and ID. Yes? How I can do that? So I need another transformation. Now I will do transformation from ABC to QD. Yeah? So I will take the current, I will measure the current. So I will measure the current. So this is the IA, let's assume. This is the IB. This is the IC. Then I will do a transformation from the A, BC, to the QD. So this will be the IQ, and this will be the ID. Now here also I need what? Theta. Yep. I need theta. Yes? Now also here I will measure the speed, tackle generator, and then I will multiply it by P over 2 because this is electrical. No, I'm assuming this is electrical. If not, I need to put P over 2 inside here.
دكتور كيف بدنا نحسب كيف بدنا نوجد ثيتا واحنا لسه مش حاسبين اي كيو واي دي؟
Yeah, according to simple thing. Y of K. This in the end of the day will be what? Will be digital control. No, no. Huh? In the end of the day, this will be no. Digital control. Let's assume that I need to calculate a simple one. Let's assume it is L di by dt is equal to U. No? Now, I need to realize it in this platform. So, one said that I will use the backward difference. Do you know the backward difference? Simply this will be L delta I over delta T equal to U. Correct? So this will be L I of K minus I of K minus 1 over Ts, the sampling time, equal U of K. Let's rearrange this equation. Rearrange this equation. In this case, you will have 1 over L, yeah, U of K over multiplied by Ts, yeah, plus I of K minus 1 is equal I of K, correct? Now, at K equal to 0, what you have? U of K will have it. Why? Because in general you are giving U of K. I of K minus 1, you don't have it, so we'll assume it's 0. Then I'm calculating what? The next iteration. Now I K minus 1 will be what? The one I calculated here are the same. Now while you are running the system, in this case omega E will be omega R. Why omega S slip is not calculated yet?
Yes.
Good? So there's a mismatch. This is the cause of transients. In general, any response has what? Transient response and steady state response. Now the transient response due to what? Due to the dynamic. The steady state response due to what? The static coupling between the system. For example, if I'm having only a resistive circuit, if I change the voltage, the current will change with no time. Correct? Why? Because the relation is what? Static. Static, static. There's no delay. There's no dynamic. Huh? Yes? Now, if I include inductor, what will happen? If I change the voltage, the current will change, but after a certain time. There will be a transient due to the inductance. After that, it will settle down, and the resistance will shape it. Here are the same. In the end of the day, I will have transient. Why? While I'm running my system, I will not capture the synchronous frame. Do you remember? I'm assuming that my flux is pointing toward where? But at the start, I don't know where the flux is actually. Correct? So the first thing what I will do, I will move my frame to capture, let's say, the rotor flux, then they will rotate together forever after. Yes? Good. So the same thing. In the end of the day, this will be what? Digitalization, digital control. Now, what you are asking, by the way, is something in the MATLAB they call algebraic loop. Yeah, algebraic loop is what? You are calculating something using something that you don't have. So, one of the simple solution for that, I will add one time delay, and I will give initial conditions to this time delay. Either 0 or I will give it what? The rated value. This will solve the algebraic.
دكتور ليش نستعمل ريفرنس فريمز ثانيين؟ هذا ريفرنس فريم convenient. ليش نستعمل ثانيين؟
You miss synchronous يعني.
Oh,
Now, in general, the alpha beta, for example, reference frame, which is the station reference frame. The station reference frame simply will transform the three-phase system to a set of orthogonal system, the alpha beta. The alpha beta reference frame. Now, in the end of the day, any reference frame, any used reference frame, either will contribute in understanding the physical system or to make the controller more easy to deal with.
oh.
Yes?
في شيء سهل الكنترول أكثر من السينكرونس.
No, this one is the, I think, is the most easy one to control the induction machine.
دكتور ليش هون مثلا بس قارنا الكرنت طلع معنا فولتج قبل بس قارنا الكرنت على طول وديناه جيت سيجنال.
Alright, just a minute. You are missing a point. If I recall back to the DC controlled rectifier or tuber, we stated that we have two methods of current control. The first one is hysteresis current control. The second one is PI control plus pulse modulation. Now, when we design the controller for the DC drive system, we stated if the current controller is hysteresis, then the only thing I need to design is what? The hysteresis band. That's it. End of the day. You cannot do anything else. Why? The system is non-linear. If I need to judge about the stability, I need to use another technique that is not given to an undergrad in order to deal with it. So in that case, I tell you what, only specify the band according how much ripple is allowed, and that's it. The second one is what? The PI control plus the PI control plus the pulse modulation. Yes? In this case, I need to design. Why? Because the system becomes linear. Yeah? So I have a method in order to design the system using the linear control theory. Yes? So in that time, I did not say that the hysteresis current control will give you voltage. No, it directly gives you get pulse. But here, the PI control will give you a voltage. Yeah? This voltage will be compared to a triangular, and the triangular will generate the gate pulse according if the reference is higher or lower than the carrier or the triangular. Anything else?
لا بس الريفرنس فريم هذا حلو. صراحة. كثير convenient كنت بطلب عشان الفلكس على الدي والكلام دائما perpendicular على ال.
Yeah, but it's valid value. And by the way, the literature we have, someone say, I will point the flux toward the stator, not the rotor. Now this one is very simple. This one, if I'm pointing the flux toward the rotor, IDR equals 0. And this will omega slip will be very simple. Huh? Now, I can do the same, pointing the flux toward the stator. In this case, lambda ds will equal to lambda, yeah? While lambda qs is equal to 0. But simply there, I need to solve the linear equation. I need to solve the linear equation in order to decouple the current. Here, it's very simple. The current is decoupled. But can it be done? Yes, it can be done. They did it? Yes, they did it. Why they did it? Because if can you do it there, you can do it there. Yeah? But what advantage? This one is more simple, more straightforward, and this one is more easy to understand and to follow. Yeah? Good. Now, another question is valid. What about if the flux is not constant? Yeah? What change will be done to the vector control? Did you understand the question? Yeah. So now I will assume the same thing. I will assume that if this is AS and this is lambda R, I still assuming that this is the DR, But lambda dr can be changed, not constant. Yeah? So the same thing here, lambda dre is equal to lambda r, but this one is not constant.
يصير مشتقة إلى value.
But still, lambda QRE is equal to what?
Zero.
Zero. Yes. So what modification I should do to the vector control? Now let's return to the rotor voltage equation. And let's discuss VDR. VDRE, which was equal to 0 by assumption value, yeah? Squirrel cage shorted, squirrel cage or one rotor shorted. This was equal to RR IDRE plus D by dt of lambda DRE plus omega minus omega R lambda QRE. Now still lambda QRE is equal to what?
Zero.
Still this one equals. But this one's not equal to 0 anymore. Why? Because I'm allowing lambda dr to be what?
Very.
So now instead of idr equal to 0, it's not. Yeah? So simply now what I have 0 will equal to rr idre plus d by dt of lambda dre. Yeah? Now I need either to substitute instead of lambda dr by idr, or I need to substitute idr by lambda dr. Yeah? Now lambda dr was equal to what? Lambda dre equal to what? L r idr e plus m I ds. Correct? So someone will say instead of idr use lambda dre minus m I dse over lr and substitute it here. Yeah. If we do so, what will happen?
R over LR.
So
1 over tau R.
lambda re will equal lr will eat lr, correct? No, sorry, r.
R. 1 over tau R.
over lr lambda dre minus m. This is IDS.
IDS.
I ds e plus d by dt. No, this is the 0. I'm mixing the two equations together. Huh? This is 0. Yeah. So d by dt of lambda dre. So I can solve with respect to what? Lambda dre. So this will equal to what now? RR over LR is 1 over tau R. So 0 will equal 1 over tau R plus d by dt lambda dre, correct? Will equal to
M over tau R IDS.
m over tau R ids, correct?
Yeah.
If equal, this means that I don't need this one. Okay? I rearrange the equation. So now I can calculate lambda dre. So lambda dre will equal to m over tau r I dse over 1 over tau r plus d by dt. This operator can be seen as s, huh? Differentiate. Yes? So simply here, this means that what? If I'm giving ID S as a reference, then if I multiply it by
and
m over tau r over 1 over tau r plus s, this s, the d by dt, if I need to implement it in MATLAB, then I will get here what?
lambda
DR.
Lambda DRE as a reference, correct? Now, do you remember the torque was equal to what? TE was equal 3 over 2 P over 2. Now it was M over LR lambda DRIQSE, correct? So now if I multiply this one by this is the constant, and this is the IQ SE, I will get what? The torque. And this constant here, K here, is this constant. So now what's the difference between the two?
I control at torque.
There, if I change the current, the ID current, the torque will affect directly, will be affected directly. Look, here it will be affected by, but after what? After the dynamo, small dynamo. There's a dynamo. Yeah? But the block diagram will be the same. Yeah? If I need to plot the block diagram. Yeah? The first thing what? I will put IDS, I will calculate lambda. Yeah? Then I will divide the torque over the lambda and the constant, then I will calculate what? The IQ reference. Good? Now the relation between the lambda and the IDS is not static, now it's done, which means that if I change the current, the flux current, the torque will be affected but after some time. Good. Good. Do you have any question? Yeah. So this is the end of this course, inshallah. You have any question? إذا موعدنا يوم الثلاثاء يوم الاثنين.